All right, so in this question, we have a mix of energy and momentum conservation stuff going on. So you have to be careful to apply the right description to the right situation. And so we're dropping two balls, and they fall together because they're going to fall at the same acceleration, and then they hit the ground and they bounce and impact each other and so on. And so our end goal is to figure out how high the small sphere sort of flies off the ground. We have to do some other stuff kind of as intermediate steps. So the first question is just how fast is the large sphere moving when it hits the floor? And this is an energy conservation question because we're going to convert gravitational potential energy into kinetic energy, right? We're going to ignore air resistance, so all the energy is going to be conserved. So E initial equals E final. Our initial energy is 3m, right, because the large sphere has mass 3m, gh, the distance it falls. And our final energy is all kinetic, 1/2 3m v, I guess I should change the notation to match, right? They call it vb, presumably for like bottom, I guess, squared. All right, so we see the 3m's cancel. We're going to multiply by 2 and take the square root. And that will solve for VB. And I'm going to write this with a capital B just because it's less messy than my lowercase b's. Right? So that's I think the easiest way. You can also use kinematics, right? We could have solved this with the kinematics equation. Right, we could have done that, and this is the exact same result. And actually, those are really the same statements. Those are really both energy conservation statements. All right, so that's part A. So now the collision happens, right? They've fallen together. The large sphere hits the ground, and it rebounds with exactly the speed it hit at. So that's a perfectly elastic collision. So this is the second picture shown. So the large sphere is moving upward with speed VB, and the small sphere, because it's fallen the same height, must have the same speed VB, but now directed downwards. And so we want to derive an equation that relates the speeds of both of them before, VB, with the speeds of each of them after, VS for the small sphere and VL for the large sphere. And so we don't know a whole lot about what's going on, but we do know it's a collision. And once you see collision, you should be thinking momentum conservation. So that's what I'm going to do. I'm just going to see if that is enough to solve it right there. So initially, right, we have Pi equals Pf, and we're going to have two terms for each of those. We have two objects moving. So initially, the large sphere, so mass 3m, is moving upward with speed Vb. And we have the small sphere, mass m, moving downward with speed Vb. So I have a negative, right? I'm going to use down as the negative direction and up as the positive. That's before the collision. After the collision, we have the mass 3m moving at speed vs, and we're told it's upward, so it's positive. And we have, that was dumb. The large sphere is VL, not VS. And the small sphere moves upward with speed VS. Right, so we keep both of them positive because of that. So the first thing we notice is that there is a m in each one of those terms. So I can cancel it. And now we can do some combining. So we have 3VB minus VB. That is 2VB. This side, we have 3VL and 1VS. And so we have now derived an equation that relates those three things we have been asked to relate. And that's it. So we're done. Momentum conservation by itself got us the answer. Which is a good thing, because I don't know what else I would use to solve this anyway. But remember, if you see collision, you should immediately think momentum conservation and see where that takes you. Sometimes that's all you need. Sometimes you need to do other things later. But momentum conservation is kind of always where you start in collisions. Okay. So now we're at part C. And so we're given one additional piece of information. We're told in this situation, so this is not always going to be true, right? For various types of balls, it could be possible that VL is not 0, right? The large ball moves upward a little bit too. But in this case, we're being told that VL equals 0. So now we need to use the relationship that we found in part B, which again was this, to determine the speed of the small sphere, that's this thing, in terms of VB, which is that. Well, this one's pretty straightforward. We were just told VL equals 0. That term is 0. So we're left with VS equals 2 VB. That's it. That's all that part is. So in the case that VL equals 0, the small sphere rebounds sort of at twice the speed that it was traveling downward at. Right? That's how it'll have to move to satisfy that. So now we need to ask, is the collision that happened elastic? And we need to justify using the results from the previous two parts. So, is it elastic is really asking, is energy conserved? If energy is conserved, then it's elastic by definition. So let's calculate it and see. So, the initial energy is made up of two parts, right? The kinetic of the 3m and the kinetic of the m. And so we know how to write these, 1/2 3m, and this is VB squared. And the other one, 1/2 times just m, negative VB squared. Notice I put that in parentheses. So we get 3/2 mVB squared plus 1/2 mVB squared, right? The negative squared goes away, and so that is just 2 mVB squared, right? That's our initial energy. Same process for the final energy. So there's two objects that could potentially be moving. However, we're told, again, VL equals 0. So the large ball isn't moving. That means it has 0 kinetic energy. Right? And the small ball, but we know what VS is in terms of VB. Right? So we can square that 2, we get a 4, divide it by the 2 from the 1/2 earlier, and left with 2 mVB squared. So our energy before the collision is that, our energy after the collision is that. Those are the same number, therefore elastic. Right? And so the way we used parts B and C was basically this, right, this substitution. All right, so we have part E. And so in part E, the collision has now been completed. We want to see how high the sphere rises, the small sphere rises. And this is back to an energy conservation statement, right? We're going to convert kinetic energy into potential. So our initial energy, 1/2 m 2VB squared. And we calculated, actually I'm going to do this the formal way. This is 1/2 m VS squared, which is 1/2 m 2VB squared. But we also know what VB is in terms of the original height, which is an important substitution. 2 square root of GH squared. I remember that answer correctly. Oops, I forgot a 2 in there. All right, square root of 2GH. So that, when you sort of expand everything all together, is that. So the 2 and the 1/2 cancel. So that's 4mgh. Right? And so that must equal our final gravitational potential energy, which is mgh, where little h is our unknown new height that it rises to. Right? And so we have 4mg capital H equals mg little h, the mg's cancel, and little h equals 4 capital H. Right, so it rises 4 times higher than you initially dropped it from under these conditions. And that's the whole problem.